Okay, so the next thing we're going to work on is what happens when a ball rolls down a ramp. So here we have a ball. It's going to roll down this ramp. Okay, and so what we want to do to start is find what's the speed of the ball at the bottom of the ramp. Okay, so I think the easiest way to approach that question is using energy, because at the top of the ramp, if it started at height h, it had gravitational potential energy. When it got to the bottom of the ramp, it's rolling smoothly without slipping, which means that it has some rotational kinetic energy, and it has some translational kinetic energy. Okay, and because it's rolling smoothly, we're assuming it's not slipping, which means that we can say that V is equal to omega R, or that omega is equal to V over R. Alright, so we'll take that and put it right there. Okay, so we get mgh equals 1/2 times, let's see, moment of inertia of a sphere would be equal to 2/5 mr squared. Okay, so 1/2 times 2/5 mr squared, and then we'll put the V over R, and we'll square it, plus 1/2 mv squared. Okay, simplify all this. This is all going to turn into 1/2 times 2/5 is 1/5 m, and then the V squared over R, the V over R squared becomes V squared over R squared. The R's cancel. We have 1/5 mv squared plus 1/2 mv squared equals mgh. Okay, the m's will cancel. All right, we're going to combine these, so we get that gh equals 1/5 and 1/2. So that would be 5/10 plus 2/10, so 7/10 v squared. So v is equal to the square root of 10/7 times g times the height of 1.2 meters. And that will tell us how fast it's going at the bottom. Okay, so we should end up with a velocity of about 4.1 meters per second. Alright, and our next step now is to find the linear acceleration. We could use this as our final velocity if we want to do some kinematics, but I'm going to use torque and net force to analyze the scenario so you have a chance to see how that works. Okay, so for this to find acceleration, I'm going to just draw a picture of the ball on the ramp. Okay, and so from the center of mass, we have gravity pulling it downward, mg. Okay, we have friction acting on this point where it touches the ground. Okay, and so we can analyze it as if it's rotating about its center of mass, and friction is causing torque, or we can analyze it if it's rotating about this point and in which gravity is causing torque. I'm going to choose this first one around the point, the center of mass, so that we don't have to use the parallel axis theorem for the moment of inertia. Okay, so we want to find acceleration. So if we look at a free body diagram, okay, of just the forces acting on the center of mass, we have gravity acting downward. Okay, we're going to have also the normal force perpendicular. We'll have friction pulling up the ramp, and we're going to have this perpendicular normal force. Okay, so I'm going to write a net force equation. M times A is equal to, we'll say that up the ramp is positive. Okay, so if up the ramp is positive, then we're going to say that, okay, there's a frictional force up the ramp, so that's positive. Down the ramp, we have the component of gravity that is perpendicular, or that is, parallel to the ramp. Okay, so remembering back, that's going to be equal to mg sine of theta, in which theta is this angle right here, the same as the angle of the ramp. Okay, and so we get this equation here relating acceleration, friction, and the gravity pulling it down the ramp. Okay, so we're going to go ahead now and look at the factors causing it to rotate. So if we're looking at the rotation here, both the normal force and gravity go through the center of mass, and so neither of those causes a torque. But this frictional force does at a distance r away from the center of mass. And so if we do a net torque equation, we say I alpha equals we're going to say it is, since it's going counterclockwise, we're going to say that's a negative torque. So negative F times the radius. Okay? Now we're finding linear acceleration, so we want to replace alpha with A. So we're going to make an equation equating angular and linear acceleration. So if up is positive, that means up the ramp is positive acceleration. For it to roll up the ramp, it would have to roll with a positive direction this way. So we can use it just like this, and we'd say that alpha is equal to A over R. Okay, so remember with previous ones, we might have had to make a negative here to make them match up. So we're going to replace A over R right here. All right, we have, we can solve this guy for friction, so F is equal to MA plus mg sine theta. We'll put that in here. Okay, and then finally for I, our moment of inertia, we're going to use 2/5 mr squared, since it is a sphere. Okay, so we'll divide that r over, and these r's will cancel with that r. We'll divide mass out. Okay, and I'm going to send a negative sign over here. So we get negative 2/5 A equals A plus G sine theta. Okay, so that I'll subtract A over 2/5, negative 2/5 minus 1 would be negative 7/5 A equals G sine theta, so that A is equal to negative 5/7 G sine theta. Okay, and so we can punch that in and calculate it, and so we get an acceleration of negative 3.5 meters per second squared. Okay, the last question here is, what was the magnitude of the frictional force? So we can take a couple approaches. We can use this equation right here, or we can use that one right here. It won't matter, let's just use this one right here. So F is equal to MA plus mg sine theta, okay, or M times A plus G sine theta, okay. The mass is 6 kilograms. Alright, A was negative 3.5 meters per second squared plus 9.8 meters per second squared times sine of 30. Okay, so that would be, since that's 1/2, this becomes 4.9. 4.9 plus negative 3.5 is going to be 1.4, and 1.4 times 6 is going to be, real quick punching in, 8.4, and that would be newtons. Okay, so the frictional force here is going to be 8.4 newtons. Okay, and you can see here that frictional force did not depend on the radius of the ball, neither did the acceleration for that matter. And if we were to think about static friction, this is not the maximum value for static friction necessarily. All this is how much force it exerted to cause it to roll. Okay, and it would have needed more force if it had a greater mass, and it would have needed, well, I guess it would have needed more force if it had a greater mass, and if it had exerted a smaller force, well, I guess it wouldn't have needed as much force if it had a greater acceleration. Okay, and then of course all of this is based on the assumption that it doesn't slip. Okay, because when it slips, this equation goes out the window and we can't do this analysis anymore.